I'm Dana Berge, U.S. Senior Engineering Manager for Luxshare-Technology. We were asked to prepare a short summary presentation of the different cable solutions currently popular in the industry for data center and enterprise applications. The organizers of the Global Summit thought that some of you might be interested in hearing about today's high-speed copper and optical cables. Some of you anyway, not everyone. That's why this is just a recorded session. Folks who aren't interested in the topic never have to click and hear me yapping. But apparently you did click, so I assume you are interested. Welcome. Let's talk about some cables. As we take a look at the agenda for today's talk, you can see that I'm shooting for a fairly high-level presentation. I'm not going to get into the deep details in each of these configurations, but I want to give you an overview, a little bit of a comparison of the different types of solutions, and some of the considerations that you may want to take into account when selecting what's going to work best for your situation, your application. So we'll start with a copper cable roadmap and take a look at some of the form factors and cables that are really just coming out now and becoming available in the industry over this past year. I want to look at two form factors specifically, the 4-channel QSFP and then the 8-channel QSFP-DD, both in direct attach and in the active copper cable solutions as well. When we do that, we'll talk a little bit about what's important to consider and what might be different from one vendor to another. These are all standard cables, and certain things are going to be the same, but others you may have some preferences. Lastly, we'll end up with a couple slides talking about optical cables, when you might consider, or when the industry does consider, active optical cables versus your standard sort of optical module solutions. Okay. Just to get on the same page, so we'll be using a lot of acronyms as always. DAC stands for direct attach cable, and that's a completely passive copper cable. Direct attach can be a bit misleading. The wires are directly attached to a paddle card, not directly attached to the contacts in a separable type connector. These are, at least the form factors I'm talking about today, have a paddle card in the mating interface. The active copper cable is very similar. Well, I'll show a breakout later that you can sort of see the same components. It's almost identical to the DAC, except that inside on that paddle card, in addition to some EPROMs that we use to store information about serial numbers, part numbers, things like that, in a DAC, in the ACC you're also going to have some equalization. So you'll have chips in there doing some type of boosting of your signal in order to achieve some greater lengths. And then in the optical cable, also even more electronics inside of the module, and we'll talk about that when we get to it. Okay. This is kind of the primary slide of the presentation, just a summary comparison of the three types of cable solutions, DAC, ACC, and AOC. And the first thing that we would look at, and sort of the primary reason to choose one over the other, is the distance that you can go. In copper cables, for example, for DACs, because of the insertion loss found in the copper cable itself, the bulk cable really, you can go maybe 5 meters for NRZ, 3 meters for 56 gig, 2 meters for 112 gig. Those are pretty standard lengths. Now, any cable manufacturer or my competition, whatever out there, somebody's going to look at these numbers that are on this slide and say, that's not right, ours is better than that, or that's not right, there's no way you can be that good. That's fine. These are not definitively Luxshare numbers. These are industry numbers. I know I've seen product out there. This is just a baseline, right? Again, you go to your favorite vendor and look for some specific information on the lengths that they can achieve and some of the other details on this page. But it's just a reference to start the conversation, okay? So as I was saying, where you're limited with the direct attach cable, especially at 112 gigabit to 2 meters, that's a pretty standard limitation discussed in the industry. With an active version of the same type of cable, you can get back to 4 or 5 meters in length. And you pay a price for that, as you'll see later on, in terms of power requirements and price. And versatility or flexibility and things like that. But if you need that type of length, you can get there with an ACC solution. The active optical cable can go much, much further. All right, and in fact, that's generally the use cases for AOC, or actually the longest lengths for are you use optical modules and you plug your cables in where you're routing fiber through buildings and things like that. You're not going to take an active optical cable and try and shove it from one place to another. But you can get, we saw a lot of 30-meter AOCs and even 100-meter every once in a while. So there are times when those kind of lengths are AOCs are selected instead of the modules. There are also cases where even short lengths someone may choose an active optical cable. If we look at the power dissipation, that's a huge consideration for many. Again, there'll be many arguments on what's achievable. These are just some numbers for comparison where we see where maybe 5 to 6 watts required for the ACC, where the AOC and maybe 8 to 10 watts. There's a little bit more happening in the electronics in the AOC. I will warn you, sometimes early on, when you have brand new chips, this happens in the folks we work with for the AOCs, you're going to draw power pretty close to what the active copper chip is going to pull pretty much the similar kind of power to the active optical cable, and it's all later then that in subsequent revisions of the chip where they work hard to bring that power down. The reason they can do that often is because we'll be working with a company who makes chips not necessarily intended to put inside of a cable, full features. And for an ACC, you don't need all those extra features. And we've found that if you remove some of the feature set, you can get to something that works great in an ACC, but doesn't require quite as much power as the full featured chips. So that's one of the things that happens and why we can achieve somewhat lower power with the ACCs. In terms of price, again, this is just ballpark. If a DAC costs you $10, an active copper version might be $40, and an AOC might be $100. That's just sort of a ballpark. You're going to find that sways back and forth for all of them. What I have found is many customers, ACC is trying to sort of fit in the middle there and find its niche. Clearly, if you can achieve the length you need with a DAC cable, that's the way you're going to go. All right, there's a lot of reasons for that, mostly price. Now, do you want to move, if you can't achieve the length you require, do you want to go to optics, or is there a sweet spot in there where an ACC, an active copper cable, might be the right spot? Some customers are saying, well, what I need it to be in order for me to consider it is slightly more expensive than the DAC, not just slightly less expensive than the AOC. Now, I'm not sure exactly what that means, and we're still working out certain kinds of or certain programs to see if we can find a good value proposition for the ACC. And in some cases, we have. With respect to weight, obviously the copper cables, you have essentially a twin axe for every channel, and maybe between 0 and 3 drain wires with each of those. So when you add all that wire together, you're going to get a garden hose by the time you get up to 16 pairs or 32 pairs. So it can be pretty heavy compared to optics. Reliability, we just have really some ballparks there, right? AOC has the most things that can go wrong, I guess. But I list it as good, better, and best. I don't have any worse on there because all of these are built to standards and are quite reliable, or they wouldn't be being used in data centers these days. So, but you will find, the ACC can be the most reliable. The bulkiness isn't always a bad thing because you can have some really good, solid, reliable, mechanically reliable cables made with DACs, and you don't have any electronics to go bad, so to speak. EMI, EMC, similar situation, right? The DAC doesn't have any internal electronics, so it can be better than the ACC. The active optical cable, you're not running any signals and trying to contain them inside of a shield of a cable. You have your optical connection, so you're not going to have cables radiating like they can in a copper solution. Okay. So slide 6 shows a copper cable roadmap, right? And it's really showing, at least with the form factors that I'm talking about today, the QSFPs and the QDDs, the 200 gig, 400 gig type solutions. A lot of them are fairly recently introduced into the market over the last year or so, and some of them are only just coming out now with respect to some of the QDD 800 gig especially. So I'm not going to go through each of these in detail, but I wanted to put this up there so you have it as a reference on what's coming out when and what's available already. This is in terms of copper, both DAC and ACCs. Slide 7 shows an expanded view of a DAC cable. Pretty straightforward, right? So you can see the bulk cable itself. Then there's and a lot, as I said before, these are governed by MSAs, SFF specifications, the electrical performance by IEEE specs. So there's a lot of things that are going to be the same or very similar from vendor to vendor. But the bulk cable itself can be different. There's a number of vendors that all buy from the same bulk cable company, so theirs will be very similar. There are other companies who design and develop their own bulk cable, and there's some special features and capabilities that you can get if you're working with a vendor that makes its own cable. Also, cable termination techniques you'll find differ from vendor to vendor. That will all give you, what we're talking about there is small differences potentially in margin. Maybe one will give you the ability to go to a slightly longer length than another vendor because of a lower loss cable or some better technique in terminating the cable, things like that. These all have back shells. MSA governs the details of those back shells and SFF specifications. Shows the paddle cards in there where the EEPROM is going to go on. In this case, for an ACC, there's just some extra electronics. Now that extra electronics in an ACC has to fit inside of this back shell, and that can be a challenge. We often find chips that were not designed for ACCs may not fit, and we have to have something special developed in our partnership with some of the silicon vendors in order to get the chips we require inside of the space constraints. Okay. This slide is intended just to be, again, as a reference to see effectively what lengths are available or are generally offered in each of the different speeds. And there's a different wire gauge, of course, for the different lengths that you're trying to achieve. The bigger, bulkier wire, you can get much lower loss and you can get longer lengths. And your longer cables are therefore going to be thicker, a little stiffer. All of that needs to be considered. Let's see what else I want to say about this one. We'll talk about it a little bit later. I have a slide or two or a slide on reliability. I'll mention some of the considerations there regarding operating temperature. Right, that's something to consider. A lot of times, the electrical performance that you might be provided from a supplier is a lab ambient temperature in a laboratory may not perform exactly the same at temp in your data center. So you're going to want to make sure you're speaking to your vendor about what's the performance in use. All right, we'll talk about that in the future. Just a couple other housekeeping. When I say 56, or I'm referring to the 56 gig PAM4. That's the industry standard for 56 gig communication. 112 gig also PAM4, and I'll bounce back and forth between calling something 200 gig, meaning it's 4 channels of 50 gig, or 400 gig, maybe 8 channels of 56 gig, or 4 channels of 112 gig. It can get a little bit confusing because we use both ways of talking about it. Okay. So this slide shows something quite important, and that's bend radius considerations, right? So it's wonderful to have this beautiful cable that's tested either straight or maybe in a nice little gentle coil in a laboratory, and it meets the IEEE spec. SI performance is wonderful. But when you go to install it, you're going to be needing to bend it in various shapes. And the first thing you're going to need to do is just coming out of where you're plugging it in, the cage you're plugging it into. You may need to make a quick turn, right, left, up, down, whatever. Especially if you want to close a door on a chassis, or if you don't want the cable hanging out too far into the hallway or aisleway. So the distance of that bend, or that's required for that bend, is quite important. You'll find that most vendors specify a bend radius of approximately 5 times the outer diameter of the cable. That's a generally very safe bend radius, and found, what's published by most vendors. So there's some numbers here based on our cables of various gauges, and what that means in terms of bend radius, as well as then the minimum space from sort of the front of the system out to the end of the cable that's protruding from it. Slide 10 lists a number of issues that one should be aware of when selecting reliable cables. It really separates good cables from not that great cables. First of all, you have to remember that when your installer goes to put all the cables in where they belong and route them, he's not going to be really gentle like your test engineer was in the laboratory, or your vendor's production line was when doing production testing. He's likely going to plug that cable in. The first thing he needs to do then is probably get some kind of a right angle bend, right? Either up, down, left, right. Then he's going to route the cable where it needs to go. Somewhere in that, he may need to get around something and could create an S-bend. S-bends can be particularly difficult on some types of cable constructions. If the cable happens to be a bit longer than he needs, then he's going to coil the excess up, right, and hang that somewhere. So the cable needs to be able to survive that kind of coiling. And lastly, when he goes to plug the far end in, he may find the connector is upside down, and he'll need to twist the cable 180 degrees. That can be a big degradation in performance on a poorly designed cable. If you look at the photograph on the top of slide 10, you can see the test fixture that we use to do this kind of complex bending and make sure that our cables maintain their superior signal integrity performance, even when routed through some of these extreme mechanical bends. The figure on the bottom, or the photo on the bottom rather, shows that we also test our cable SI performance at temperature. And we'll measure the SI performance at 25C, room temperature, 45C, 65C, 75, even 85C, to make sure that there's not too much degradation in SI performance. You're always going to see higher insertion loss at higher temperatures. You need to make sure that you have enough margin based on your operating temperature, and make sure that your vendor does that kind of testing and can ensure that their cables are going to work in your application. I have one figure here at the bottom, or a photograph at the bottom of the slide as well, that shows something that we do to fix yet another issue. It's not just the degradation or potential issue with the bulk cable when you do a bend, but the bend also can put some pressure on the mating interface of the connector. We've had a number of customers that are concerned and have seen issues because of that, especially on the thicker cables. This is a tiny one I'm using for the demonstration, but the big cables can put some really severe forces on there, and we've seen customers who have issues with, or signal integrity performance issues and reliability issues because of that. What I show on the slide is something new to the industry as well, and that's a pre-bend, where there's a structure put on the cable to put, if we know ahead of time which way it needs to bend, that bends the cable before it's assembled, so that the stresses are removed and it's not going to be pulling on that mating interface. So that's something that was quite interesting to some customers, and something you may want to consider as well, depending on your applications and the issues involved. Moving on, I have a number of slides that show signal integrity performance. For your reference, again, they don't represent the very best cable, the very worst cable. They're just sort of an average cable that you can find in the industry. And you can see how for the slightly longer cables, we generally move to a larger wire gauge. In fact, the ones I'm showing on the screen are pretty common. For your 1 meter cable lengths, you'll generally see a 30 gauge cable, 2 meters, maybe 28 gauge, and 3 meters, 26 gauge. This is for 56 gig performance. Then I also show a functioning or working active copper cable as well at 56 gig. These are just to show they actually exist, they actually do work, and an example of such. Then there's some signal integrity performance for 112 gig. At 112 gig, we'll often be working exclusively in 26 gauge just because of the higher losses at that frequency. But there are some cases where we do provide, for the very shortest cables, some smaller lengths. You may ask, well, why don't you go to something bigger than 26 gauge if we're getting close to the edge? Instead of going to an active cable, why can't we just use a bigger, thicker twin ax? The problem is 26 gauge is about the biggest cable you can fit into the connector module itself. You're just getting too much wire in there. You're not going to be able to fit it on the paddle card. Mechanically, it's not going to work. So that's the limitation you'll mostly hear talked about for 112 gig is 26 gauge 2 meters. I don't show an active cable at 112 gig, but we have samples that will be shipping to a customer very soon, so I know that there are some, they're being evaluated at certain customers for 112 gig. The second example form factor I wanted to show was QSFP double density, or QDD. Just a couple things I wanted to note about this form factor. You're doubling the number of channels, hence you'll see in this diagram there's actually two 8-pair cables that are used and that can fit inside of the shell. There are other implementations of this, and I list that there for your 56 gig. You can do the 2-pair. You can also do a 16-pair. And a 16-pair jacketed cable or PVC cable is very new to the market, and we're offering that right now. At 112 gig, you're generally in the nylon mesh 16-pair cables, which is your more common solution for 16-pair. You'll take the individual pairs, put them inside of a metal braid, and then put a nylon braid over top. Jacketed, there's just some advantages to a jacketed cable, but it's very difficult to do, and that's why they're fairly new. I have a slide that shows sort of what's out there now in the industry for double density and what's coming. And of course the bend radius information. Bend radius, when you're using the two 8-pair cables, very similar to a single 8-pair cable because they can shift and give you the bend, and it's really just one getting in the other one's way that extends the distance a little bit further in some bends. If you use a nylon braid, you might think, well, that should be really flimsy and flexible compared to a jacketed cable. But you need to be careful because you want those twin axes to bend in a right way bend, right? If you bend two wires in the good way bend, as we call it, you'll do very little damage to it. If you try and bend them in a bad way bend, then you'll start to degrade performance. And if you just have them in a nylon mesh inside of a braid, it's harder to control how they sit, and you want to be a little bit more careful in doing a sharp bend than if you have a jacketed cable where they're always positioned where they're designed to be. And in fact, if you look at the drawing I have for a 1x16 PVC cable for our 30 and 28 gauge, now note here we are showing a minimum bend radius as 3 times the cable diameter. That's something that we use a little bit different than most of the industry because of the quality of our twin ax cable and the ability to really bend them. You can bend them almost back on themselves, even tighter than the 3X, without degrading the signal integrity performance. Okay, again, I have some slides just for your reference on signal integrity of a QDD and an ACC cable. That's the 56 gig, 5 meters. And on slide 21, I'm showing some photographs of a demonstration that we had at DesignCon for actually a number of years. We've been developing these types of ACCs. And this one is showing an actual retimer type solution. So a smaller 28 gauge cable, 5 meters, and it's working error-free. So the photographs in the demonstration here are actually showing some test boards and a DAC cable, and then with the silicon vendors boards. So just a proof of concept kind of effort. But now we are actually, and the data shown here, is from an actual ACC cable. So, okay, let's move on to optical. And active optical cables have been widely used in HPCs. Lately, they've become more popular in hyperscale enterprise and data centers, mostly because of the extended, not just because they have extended reach, but because the copper at higher and higher speeds has such limited reach. That's one of the reasons that that optics is and optical cables, active optical cables, are becoming more popular for some shorter lengths, where in the past it was always copper. Obviously, with respect to the active optics, there's transceivers that convert the electronic or electrical signals into flashing laser lights, which then are the signals transmitted over the fiber optics cables. I show on this slide 22 sort of the normal longer reach solution, which is pluggable modules or optical transceivers, which have a port to plug your fiber optic cable into. The active optical cable has the fiber bonded permanently into the end of the transceiver, so it creates essentially module to module kind of cable assembly, just like the copper solutions that we've been talking about. Main benefit obviously is you can go further, right? So if we look at the benefits of active optical cables, there's some benefits over transceiver solution in optics, and there's some benefits over copper solutions. First of all, they're the lowest price optical, meaning you can get an active optical cable at a lower price than two transceivers and a solution. It's a pretty straightforward plug and play, just like DAC cables. You can go up to 100 meters. Now usually it's lower than that, 30 meters and under for active optical cables, but we do sell 100 meter quite often. The active optical cable has a bit lower power consumption than an equivalent two transceiver solution, and you don't have any optics to worry about and clean. It's all inside and permanently connected. And lastly, either of the optical solutions have one benefit over the copper that can be considered, and that's that it isolates electrically the systems. You don't have any ground loop issues that you can have a problem with in the copper-based applications. Okay, I'm running out of time, so let me wrap up. I have a number of similar slides for optics. I show an optical cable roadmap from which you can see what's currently available, what's coming out on the market right now. I have an exploded view of the AOC. It looks a lot like the other cables, right? The only issue is now there's some electrical to optical, TOSA, ROSA type electronics there. There's some fiber cables inside. So it's a little bit more complicated, hence it's a little bit more costly, but it's the same idea. If we take a look at the bend dimensions, we'll find that they're very similar actually to the copper solutions that we've already looked at. Now, your fiber you may not want to abuse quite like you do the copper cables. I talked about some of Luxshare's DAC cables that you can bend almost directly back on itself without doing much damage or any no degradation of the signal integrity. You may not want to bend a fiber cable quite that hard, but the fiber cable is so much smaller and lighter. It's very attractive in terms of being able to handle it and route it and take care of things. So depending on your needs and your lengths, your reach lengths, you have several options. Lastly, I have a number of slides that simply show the types of optical cables that are out there. I did not really mention breakout cables and splitters, but they're a common active optical cable solution as well, breaking out from, for example, a QDD to 2 QSFPs or 4 SFPs or something like that. Those are common in the industry as well. And then I will show a bunch of sort of the applicable or similar transceiver module solutions. Then lastly, we come back to the first slide that I showed, just as a reminder of the kind of comparison between your direct attach, your active copper cable, and your active optical cable. There's sort of a use case for each of those, and it really depends mostly on reach, and where there's an overlap, then there are other reasons to choose one over the other. I just wanted to give you sort of a basic overview of these things that should be considered. You should work directly with your vendors. I'm sure any of them would be just happy to provide you with more data. We would be happy to provide you with more data. We'd also be happy to provide you with a quote. Thank you very much for listening.